Wide-bandgap devices offer the potential to operate at higher temperatures, higher blocking voltages, but also higher switching frequencies compared to their silicon counterparts. And especially the high switching frequencies are a problem when it comes to the real-time simulation of switched power converters. Because there, any switching event will in general not coincide with a fixed model step of the simulator. And this includes natural commutation, but also forced commutation of devices. My name is Niklaus Felderer, I'm from Plexim, and today we're going to look at a possible approach on how to solve this issue. And we're going to look at the particularly challenging case of DC-DC converters, and we take the dual active bridge as an example. So let's look at the generic hardware-in-the-loop setup. We have a microcontroller that's attached to the real-time simulator, and the controller is going to send out the PWM signals that's read in by the simulation platform. Now here, the model discretization step size of the plant is naturally limited by the fact that we can't compute the model infinitely quickly. So this means if we only sample the incoming signals once per simulation step, and we try to reconstruct basically all the information of the pulse train inside the model, then we'll do quite a big error. And this sampling error, depends on the ratio of the switching period to the model step. This is also what we see here in the slide. We have the incoming pulse train with a certain duty cycle, and then we only sample the incoming signal once per simulation step or per model step, and we'll see that the estimated duty cycle, d tilde, is now much different. So what can we do about this? We subsample the incoming signal to get a higher temporal resolution. And if you build an average value from the subsamples, we have one value that keeps the volt-seconds information of the original signal, which is basically the area under the curve. This is called a time average method and has been proposed by Peter Lane and his group, well, nearly 20 years ago, and is quite a standard. Now, most of the time, this average unit will actually produce values of 0 and 1. Only when a switching transition happens in a model step, the unit will produce values between 0 and 1. So how can we use these average values for the simulation of the switched power converters? We need special converter models that can deal with the situation when the averaging unit produces an average value between 0 and 1. So this is where the special hybrid models come into play. These models are based on controlled voltage and current sources and can deal with the average value between 0 and 1. They also include a diode pair at the phase output to distinguish between negative and positive phase currents. And this is a very important feature, so this diode pair, because it is needed to basically model discontinuous conduction mode, for example, or the reverse charging of the DC link over the anti-parallel diodes. If you didn't have those, then you were quite limited in the range of operating points you could represent. Now, this important point is also one of the weaknesses of the model, and this is because the diodes can only switch once per model step. And in real, obviously, they can switch whenever this is given by the circuit condition or by the operating point. And so this leaves basically an inaccuracy when you simulate. As mentioned in the beginning, this is especially a problem when looking at DC-DC converters, where the current changes direction at the same rate as the switching signals. Let's take the dual active bridge. For example, if this operates at 100 kHz and 1 microsecond step size, then there are only 10 data points in one model step. Now, this is a problem because the time resolution on a zero crossing is very much limited. And additionally, there are actually 2 zero crossings per switching cycle, and also the modulation will include that time. Now, what you see here is the leakage inductor current, and here actually the zero crossing detection is important, but what is even more important is the current that's drawn from the DC link, because they will affect the voltages, and the voltages are the quantities that we are controlling. So what are the possible solutions? What can we do to tackle this? Now, one can try to compute faster, but this will still limit the resolution on the zero crossings to some extent. Right? You can't calculate infinitely fast, and basically you're limited by the hardware capabilities and maybe also the model that you're using. To compute faster, one can implement special converter models, but often they rely on switch models with numerical snubbers. So these snubbers, they do have some drawbacks. Obviously, this is a very nice approach because it's nicely scalable. But again, the snubbers, they might bring in new problems. One could also try to simplify the dual active bridge model, but this will limit the range of test cases, which is really contradicting the purpose of the hardware-in-the-loop testing in the first place. So what we aim for is a converter model with ideal switches that do not have any snubber parameters, and this should also be able to switch arbitrarily inside a model step, basically these diodes. So the concept is called sub-step event modeling, and the name will be clear once we go through the complete calculation of one model step. So this sub-step event model replaces the switching network and all the energy storing elements to directly implement a more accurate integration scheme that takes care of all switching events. So basically what this means is we replace the model and add a model that's able to really react and change switching states during one model step. The inputs of the model are the DC side voltages and forced switching events, so the incoming switching signals, and the outputs are the DC side currents. Let's look in detail at the calculation of one complete model step. So first we start by reading in the switching signals with a very high temporal resolution and put any switching transitions into an event queue. So let's consider the following case for the dual active bridge that's shown here on the bottom. There are two switching events happening at T1 and T2, but these are of course not the only switching transitions that will occur. If the leakage inductor current is close to zero, there will also be natural commutation of the diodes. So these are not shown here, and this is what's actually coming now in this sub-step event calculation. So to understand this, let's make a specific example where we calculate one full model step, and let's start off with an inductor current that's close to zero and is positive. So if the following switches are active, the inductor current will fall due to the negative voltage over the inductor. This is what we see here in the graph. We have a falling current, and important is now that the inductor current will go through zero at some point. And if we calculate the slope, or if we take the slope, we can calculate the zero crossing of the current. So this zero crossing event marks the first so-called sub-step that we need to perform. After the zero crossing, the derivative remains the same and the current falls until the next scheduled event, which is the beginning of the dead time interval. So in the next interval, this is the second sub-step. Now one could argue and say, well, why do we even need the information on the zero crossing if the derivative does not change in the second sub-step? As you can see here, the current continues to fall with the same slope. Now, this is important because we need later to calculate the average current that's drawn from the DC side capacitors, and there the information on the zero crossing is crucial. We finished the second sub-step at the beginning of the dead time interval, and now what happens is important because we are entering the dead time of the primary side full bridge, and we have now a positive voltage applied to the inductor, and we will have a rising current. If this current goes to zero, then actually all switches are off, and also none of the diodes will conduct anymore in this primary side full bridge. So once the current reaches zero, it actually stays zero until the end of the dead time interval, and this is the sub-step number 4. So after this fourth sub-step, we enter the next sub-step, and we engage here or give here a 1 to the switches S1 and S4, and the voltage over the inductor becomes positive again. So we have a rise of the inductor current. The last interval lasts until the end of the model step, which is indicated by the discretization step size T-disk. So if we compare this to the calculation of the hybrid model, then one can clearly see that this leads to an inaccurate value of the current. There's still some resolution and some accuracy, at least the slope or the direction of the current is correct, but we miss so many switching events that one cannot really expect this to be an accurate calculation because really of the switching of the diodes. The force commutation, or let's say the gating signals, are taken into account inside this subcycle averaging approach, but it's still not as accurate as this substep event calculation that we just did. So actually the error in the value of the leakage inductor current is not even the main problem. The critical point is the calculation of the DC side currents, and this will affect the voltages, and this one is, as we said, the main variable to control in the system. So let's look at how this is here in comparison. We have here on the top, we have the current values for the leakage inductor, and here we calculate the DC side currents. And what we basically need to do is we need to calculate the area under the curve and then average it over one model step. Then we can make sure that we take the right amount of energy out of the capacitor or into the capacitor. You can clearly see that the hybrid model leads to a completely wrong result because, again, not only the data points are wrong, but clearly the area under the curve is completely different to what you have in the substep event calculation. So let's look at the real-time performance. So basically the setup is the same as given here. We have the real-time simulator, we have a Piccolo launchpad microcontroller, and this will send out the phase-shifted PWM signals to the dual active bridge model. And now we said that the ratio of model step to switching period is the key parameter. For this we performed two simulations, one with a ratio of 50 and one with a ratio of 5. So for the first scenario of the ratio of 50, both models behave very similarly. For this application, both DC links are modeled with a fixed voltage source, so this is a very ideal setup. And in such a simple scenario, both modeling approaches work completely fine. Now obviously the ratio will be much smaller, especially when you look at converters using wide-bandgap devices. When we increase the switching frequency to 100 kHz, then one can clearly see that the issue with the standard hybrid model is apparent. The DC side currents are completely off, and it is merely a coincidence that the DC voltages are only around 6% off the reference simulation. So in green you can see the variable step reference simulation in Plex, and we really try to compare now of these different models the performance regarding the output voltage. On the other hand, the substep event model correctly calculates the DC side currents without a large beat frequency. So the beat frequency is here clearly visible in the hybrid model. If we look at the error in percent for different ratios, then we see that the substep event clearly performs better, and this is really our goal, to keep this CPU-based approach, but having much higher resolution than what we have basically as a model step. So even with only 5 simulation steps per switching period, the error of the substep event model on the low DC voltage side is below 2%. So to summarize this, with the substep event model, we are searching for a way to increase the simulation accuracy of DC-DC converters. We had the dual active bridge as an example, but this also applies to, let's say, a topology like the LLC or the phase shift full bridge converter. We really want to keep the ideal switch approach while still being able to interface easily to the CPU-based simulation. And this keeps model fidelity high while at the same time producing the required simulation accuracy of these topologies to really have some conclusive results from your hill tests. So one of the drawbacks of this model is that the substep event model is slightly more time consuming to compute if you compare this to the hybrid models. And this is actually not a problem because the effect is easily compensated by the fact that the substep event model is much more accurate than the hybrid model. So a slight increase in the simulation step is in this case not a problem, but actually leads to even more accurate simulation results. All right, so this concludes my presentation. I hope you found it interesting. I say thank you, and we see each other in the question and answer session that's following after this presentation or after this video. Thanks very much, and see you there. Bye.